Hello everyone, I am Amar Bharti, a PhD student in IIT Bombay. I am working in the group of Professor Gopal Dikshit. I am going to talk about high harmonic spectroscopy of nonlinear anisotropic anomalous Hall effect in topological material, particularly Weyl semimetal. I will briefly describe the topological materials. Topological materials are the newest addition in the wide variety of condensed matter systems. It has many exotic properties. One such example is topological insulator, shown here. As we can see here, there is a gap between conduction and the valence band, which make it an insulator. However, since it is a topological insulator, it has conducting surface state also, which is shown by the green line. These conducting paths are immune to perturbations such as temperature or strain. It only depends on the topological state of the material, which is given by Berry curvature. This means that even in the presence of external perturbation, conductivity of these surface states remain the same as long as the gap is open in the case of topological insulator. Such a topological protection is essential feature of all the topological materials like Weyl semimetal also. Other topological materials are topological superconductor and topological semimetals. One of topological semimetal is Weyl semimetal. Study of strong field-driven topological materials have recently started. Using high harmonic generation in these materials, it has been shown that it is possible to distinguish between topological and trivial phases of matter. It has been also observed that non-integer high harmonic generation in a topological insulator when driven by strong laser. Also, unique signature of surface state can be recorded in HHG spectra. Few cycle driven Weyl semimetals have shown anisotropic band population. Continuous effort is being made to explore and understand these phenomena. Now we will look at the Weyl semimetal, which is another type of topological material and focus of our study. Weyl semimetal has degenerate points which are known as Weyl nodes. The linear dispersion around the Weyl nodes correspond to the Weyl equation in the high energy physics. Here on the left, we have the band structure corresponding to two-band model Hamiltonian. Conduction and the valence band touch at 2 points only in the whole Brillouin zone. These Weyl nodes have topological protection against opening up a gap between the bands. These Weyl nodes are the source and the sink of the Berry curvature, which acts like magnetic field. Hence, Berry curvature leads to Hall effect in the Weyl semimetal without any external magnetic field. As we see on the right, Berry curvature vector are plotted on the top of the energy contours, where we can see the sink and sources of the Berry curvature vector. Plus and minus sign correspond to the two Weyl nodes. It also signifies the associated Chern number and the chirality of the Weyl nodes. Now we ask that what happens if Weyl semimetal is driven by strong laser. Here let's look at the harmonic spectra. We have used linearly polarized laser of nearly 100 femtosecond. It has wavelength of 3.2 micrometer and intensity 10 raised to power 11 watt per centimeter squared. We find that when laser is linearly polarized along x direction, we have harmonics only along x direction only. However, when polarization is changed to y, we have harmonics along y direction, shown in blue, but also we have harmonics perpendicular to the polarization direction of the polarization of the laser. So we get anomalous harmonics in the z direction also. Similarly, in the case of laser polarized along z direction, we get harmonics along z direction, which are normal harmonics, and also get anomalous harmonics along y direction. So we can see that anomalous harmonics are anisotropic in nature. Anomalous harmonics only produced when laser is polarized along y direction or z direction, but there are no anomalous harmonics when laser is polarized along x direction. So we ask this question that what decide the direction and the magnitude of the anomalous harmonics? The answer is Berry curvature. However, more important question is how anomalous harmonics are related to the separation between the Weyl nodes. Now let's see how. If we change the K0, which represent the separation between Weyl nodes, from 0.2 to 0.3 shown by solid and the dashed line, intensity of the anomalous harmonics decreases significantly, which is shown here. This is for Y polarized laser and Z polarized laser. The separation between Weyl nodes is directly related to the non-trivial Berry curvature in the Weyl semimetal. Hence, the intensity of the anomalous harmonics decreases when separation between the Weyl nodes is changed. However, normal harmonics for both K0 remains almost same as shown here for different polarization of the laser. Hence, magnitude depend upon the separation of the Weyl nodes for anomalous harmonics. Odd harmonics due to Berry curvature is shown for the first time in our result. It is possible due to the time reversal symmetry breaking in the Weyl semimetal. The presence of anomalous odd harmonics allow us to tailor the polarization of the emitted harmonics, which can be further controlled by the separation of the Weyl nodes. Here the time domain plots of the third and the fifth harmonics is shown when laser is polarized along Y. We find that elliptical harmonics are produced even when linear driver are used. Now let's recap the major findings. This is the first report where non-trivial Berry curvature leads to the generation of anomalous odd harmonics. As we have demonstrated, the X polarized laser leads to the generation of only normal harmonics, where Y and Z polarized laser leads to the generation of anomalous odd harmonics. Moreover, anomalous harmonics is sensitive to separation between the Weyl nodes. Thus, present work unequivocally demonstrate strong laser-driven nonlinear anisotropic anomalous Hall effect. Weyl semimetal also offer a unique platform to tailor the polarization of emitted harmonics, as the strength of the anomalous odd harmonics can be controlled by the incident laser polarization and the separation between the Weyl points. If you would like to know more about our work, then you can read the full story in our recently published paper in PRB. I would like to thank Professor Gopal Dikshit and Dr. Mridul MS for their support and help. Thank you for listening.